Hello everyone, welcome back to my channel. So in today's video, we'll be discussing how to apply Dijkstra's algorithm for a directed graph. In our previous videos, we have seen how to apply the same algorithm for an undirected graph. Now in this video, we'll be dealing with it, but in case of a directed graph. So first, let me write a formula kind of thing that we'll be using in this. That is distance of my vertex u, which is my source vertex, plus the cost of going from u to v. V here will be my destination vertex, should be less than the distance of v. That is my destination vertex. If it is less, then we will be updating its value. Okay, so the first step that I'm going to do here is, first let me write all the vertex. Now I'm going to start with my source vertex first. Now in this case, I'm assuming my vertex A as my source vertex. So in Dijkstra's algorithm, it says that it is a single source shortest path kind of problem. So you have to select one single source, that is one source vertex, and from that you are supposed to find the shortest path. Okay, so you're supposed to finalize your source vertex in the starting itself. You can select any vertex from A, B, C, D and E. I have chosen the vertex A as my source vertex. So first I will write my source vertex, then I can write the other vertices in any order. Right, so let us just go by the convention, that is A, B, C, D and E. Okay, and let me write my source vertex A over here. Now what I'm going to do is, first I will be updating the distance value for all these vertices. Now since my source vertex is A, now distance of going from A to A, I'll put it as 0. Now for all the other vertices, I will be initializing the distance as infinity. This is my first and foremost step, and this will be same for all the problems. This step is not going to change. You will take the distance of your source vertex as 0, and for all the remaining vertices you will take the distance as infinity. Okay, and now you're going to apply this formula for the next vertices. Okay, so now you have to see the vertices that are directly attached to A. Okay, and you have to see the outgoing vertices, right? So suppose A is attached to B, A is attached to C, and A is attached to E as well. But you can see that the vertex, when you're attaching A to E, the vertex, that is the direction of the graph, direction of the edge, is towards A. That means you cannot say that it is going from A to E. It is not going from A to E, it is going from E to A. So you have to see all the outgoing edges from A, right? That is the edges that are coming outside from A, not the ones that are incident on A. So the ones which are outgoing for A is A to B and A to C. So I will be considering these two vertices, and I'll be putting this formula. So here, suppose when I'm checking for A to B, A becomes U and B becomes V. That is, U, as I told you, is my source vertex and V becomes my primary destination vertex. So first I'll put the distance of A. Now from this table you can see distance of A was 0. That is what I assumed it to be. So 0 plus, what is the cost of going from A to B? The cost of going from A to B is 10. So all these values which I have mentioned in green color, they are the cost. They are the cost of going from one vertex to another vertex. So in case of going from A to B, the cost is 10. So 0 plus 10 is 10. Now this 10 should be less than the distance of V. Now what is the distance of V? From the table, if you see, the distance of V is infinity. That is what we assumed. Is 10 less than infinity is the question. Yes, 10 is less than infinity. So I will be updating the value or the distance of B as 10 in my table. So I have gone from A to B. That part is done. Now let me move from A to C. Okay, now A becomes U, C becomes V. Let me rub this. So now I'll take the distance of A. What is the distance of A? Distance of A is 0. 0 plus the cost of going from A to C. The cost of going from A to C is 5. What is 0 plus 5? That is 5. What is the distance of C? The distance of C from the table is infinity, which we assumed. So is 5 less than infinity is the question. Yes, 5 is less than infinity. So now I'm going to update the value of C as 5. And now whatever the leftover nodes are, I'll write their value as infinity as it is, because D and E is not directly connected to A. E here is connected to A, but it is an incoming edge, okay? And we have to see only the outgoing edges. And as in case of D, D is not directly connected to A, so I'll take its distance as it is from the previous step. And now I'll be writing all these distances. Now why am I not writing the distance of A over here is because A is already a visited vertex, and the visited vertices will be written on the left side. And for visited vertices, you won't consider their distances. Okay? Now you can see this is my second level. Now in this certain level or in this certain row, you have to check or you have to find or search for the minimum value. Okay, the minimum value you have to search. Now what is the minimum value in this case? The minimum value you can see clearly is 5 over here. In 10, 5 and infinity, the minimum value is 5, right? It's very simple. So 5 here is my minimum value, and minimum value of which vertex? It is for the vertex C, right? So C becomes my next source vertex. So let me put C over here. Now let me check all the outgoing vertices from C. So outgoing vertices from C is C to B, C to D and C to E, right? These are my outgoing vertices. And as in case of A and C, that vertex is an incoming vertex, but I'm supposed to find only the outgoing vertices. So I'll apply the formula on the outgoing vertices from C. So let me check first from C to B. So what is the distance of C? Now C becomes my U, that is my starting vertex, and B becomes my V. Okay, this is U, this is V. What is the distance of C? The distance of C from the table, as you can see, the current distance of C is 5. Okay, 5 plus, what is the cost of going from C to B? The cost is 3. From the diagram you can see it is 3. Now what is 5 plus 3? 5 plus 3 is 8. Now 8 should be less than the distance of B. What is the current distance of B? From the table you can see it is 10. So 8 is less than 10. Now when you get a distance which is less than the previous one or the present one, you are supposed to update it. So I'll update the value of B as 8. Now suppose I would have added numbers over here and I would have got a number like 11 or 12. Now this number is greater than 10. So in that case I will not update it. So since I got a number which is less than 10, I'm going to update it. So C to B is done. Now I'm going to from C to D. Okay, so from C to D, when I'm going, C becomes U and D becomes V. The distance of C from the table, what is the present distance of C? 5. 5 plus cost of going from C to D. From the graph, you can see the cost is 9. What is 5 plus 9? 5 plus 9 is 14. Is 14 less than distance of D? The current distance of D is infinity only from the table. So 14 is less than infinity. Yes. So you're going to update the value of D as 14. Okay. So C to D is done. Now let me go from C to E. C becomes U, E becomes V. Distance of C from the table 5. 5 plus cost of going from C to E. From the graph it is 2. 5 plus 2 is 7. What is the distance of E? The distance of E from the table, that is current distance, is infinity. Is 7 less than infinity? Yes, it's less. So update the value and make it as 7. So you can see here we have checked all the outgoing vertices from C, that was B, D and E, and we have updated their values. So now this part of C is done. C is also a visited vertex. Now check this 11 and check for all the values that are less. Now I won't be filling the boxes for A and C, because if you see on my left hand side, A and C are already visited. So the ones that are visited, I will not write their distances, okay, because that is already done. We will not be talking about the visited ones. So out of all these leftover, that is B, D and E, which is having the minimum value? You can see out of 8, 14 and 7, 7 is the minimum value. So I'm going to consider 7, and 7 is the value of E. right? 7 is the value of E. So E becomes my next source vertex. Okay, let me write E over here. E is my next source vertex. Now, what are the vertices that are going from E? From E, you can see we have A, that is an outgoing vertex, and D is an outgoing vertex. Again, we won't consider C because C is an incoming vertex, right? So outgoing edges are A and D. So I'll consider these two outgoing edges and find the value. So when I'm going from E to A, let me consider E as U, A as V. Distance of E is from the table. Distance of E. So the distance of E was so the main question is we are going from E to A. Now the thing here is, one thing which we did not notice was A is a visited vertex. You can see here A is a visited vertex. And whenever we are dealing with visited vertices, we will not be considering them. Because once they are visited, we are not supposed to again bring them back into our minimum spanning tree. So I will be ignoring E to A and I will be checking for E to D. Okay, now since you can see here D is not a visited vertex, so I can check for E to D. Now E becomes my U and D becomes V. What is the distance of E? The distance of E, that is the current present distance from the table, that is 7. 7 plus the cost of going from E to D. From the graph you can see the cost is 6. 7 plus 6. What is 7 plus 6? It is 13, right? Now what is the distance of D? 13 should be less than the distance of D. Distance of D from the table is 14. Is 13 less than 14? Yes, 13 is less than 14. Correct. So we have to update the value of D as 13. Okay. So we have covered the vertices. E was going from E to A and E to D. But since A is already a visited vertex over here from the left hand side, we are not supposed to consider A. Okay. Now we'll be considering D and that was already done. So the vertex E has been covered. Now look at the table. So if you see the table, you have only one value over here. Does that mean you have to stop your problem? No. You have to check all of these. See, first if I check A is already a visited vertex. So nothing to fill in that block of A. Okay, leave it as it is. In case of B, now what happens here with B? B is neither a visited vertex nor was it directly attached to E that I could find and update its value. So what I'm supposed to do, I'll just bring the value of B as it is. That is, the value of B was 8 previously. So I'll just bring that 8 down to my next level and the current value of B will remain same. That is, it will remain 8 only. Now in case of C, if you see, C was a visited vertex. Now I am supposed to ignore the visited vertices, so I will not fill anything for that block of C. In case of D, I have already updated the value of D. In case of E, E again is my visited vertex because you can see here from the left hand side, E is a visited vertex, so I will not be updating its value. So you're going to ignore that. So all the visited vertices need to be ignored, right? So we have two values left, that is for B and for D. Now among these two values, we are supposed to see the minimum one. So it's very clear that the minimum one here is 8. Right, out of 8 and 13, 8 is the minimum value and that value belongs to vertex B. So now I'll be checking vertex B. So vertex B is going from B to D only, right? You can see here vertex B has got only one outgoing edge, that is from B to D. There are two incoming edges from A and C which are not supposed to be considered because we see only outgoing edges. So we will see from B to D. Here B becomes U and D becomes V. What is the distance of B? From the table you can see the distance of B is 8. Plus what is the cost of going from B to D? Cost is 1. 8 plus 1 is 9. Now is 9 less than the distance of D? The distance of D was previously 13 from the table. Now is 9 less than 13? Yes, 9 is less than 13. So now I'm going to update the value of D as 9. So from the graph and from all of this calculation, my value of D has been updated as 9. So now I have got this A level because now you can see that I have seen all the outgoing vertices of B. Now time to check. Now should I add the should I update the value of A over here? No, because it is a visited vertex. Okay, here B comes because B was the vertex. Now should I visit and should I update the value of B? No, because it is already visited. Should I do that for C? No, because it is already visited. Here is the value of D. This is now my new visited vertex. And should I update for E? Again, no, because it is already a visited one. So now I have got one more value, that is 9. Okay. So here I can stop my problem. Now suppose if you ask me, suppose I have to go from vertex A to vertex D, right? So if you ask me what is the minimum, if I have supposed to go from A to D, now you'll ask me what is the minimum total edge weight. Now the minimum total edge weight will be 9 if I'm going from A to D, right? So that is how you find out. Now suppose if I want to go from A to C, then the minimum edge weight will be 5. If I want to go from A to D, it will be 9. If I want to go from A to E, it will be 7. If I want to go from A to B, it will be 8. So the circled ones are the minimum edge value if I want to go from that particular source vertex to that particular vertex, right? Now suppose if I'm going from A to D, but I want to know what is the path of going from A to D. Now let us see how to find the path. Okay, going from A to D. We know that when I'm going from A to D, my total minimum edge value will be 9. But what is the path that I have to follow so that I get this minimum edge value? So for that, first I am going to tell you how to find the path. So first you will write D as it is, which is my destination vertex. So now you have to see the table for the path. So D here is my current vertex that I have written over here. Now I'm going to put a pointer over there and the value of D is 9, right? Now I'm going to move that pointer to the previous step, that is the previous level. Now I've moved the pointer to the previous level. Now if you see, at the current level the value of D is 9. For the previous level the value of D is changing. Now if the value is changing while moving the pointer, then you have to see the whole level. And when I see this whole level, I have to find the minimum value in this whole level. The minimum value in this whole level is 8. So now I'm going to put my pointer at 8. Now 8 is the minimum value for which vertex? 8 is the minimum value for vertex B, right? So I'll write B over here. Okay. Now I'll take the pointer to the previous level again. Now I'm taking the pointer to the previous level. Now if you see, the value of B has not changed, right? It has not changed. So like how I checked this whole level and I checked for the minimum value, I will not check this level for the minimum value because the value of B while moving the pointer has not changed. Suppose if the value would have changed to some other number other than 8, then I would have checked this level again. I would have found out the minimum value and put the pointer at that location. But since the value has not changed for B, I will let the pointer remain as it is and move to the previous level again. So now I'm moving to the previous level. Now I see that the value of B has changed. Now it's time to check the whole level and check the minimum value at the whole level. The minimum value at the whole level is 5. So put the pointer at 5. Now 5 is where the pointer is and 5 is the minimum value for which vertex? For vertex C. So put C over here. Now again move the pointer to the previous level. Now you see that again the value of C has changed. From 5 it has changed to infinity. So again I'm supposed to check the whole level and see for the minimum value. The minimum value is 0, which is the value of A. So put the pointer at 0, right? And now add A over here. So the whole concept here is when you put a pointer to a certain level and when you are moving from that level to the previous level, if the value of that particular pointer changes, then you're supposed to look at that whole level and see for the minimum value and shift the pointer to that minimum value. Suppose the value is not changing, then you should not look for any minimum value in that level. Just keep on shifting the pointer to the previous levels. So this is how you find the path. So I'm just going to reverse it and write as A, C, B and D. So when I move using this path, I'm going to find this as my minimum weight. That is, let me add it and show it to you. When I'm moving from A to C, what is the cost? If you see from this graph, when I'm moving from A to C, cost is 5. Then when I'm moving from C to B, when I'm moving from C to B, the cost is 3. Plus when I'm moving from B to D, the cost is 1. So 5 plus 3 plus 1 is 9. And 9 was our minimum cost, right? So you can see here we have got the answer, the 9, which is our total minimum edge weight. So this is how you can find out the path from A to any vertex. Okay, follow the same procedure and find the path from A to any vertex. So that's all for this video. This is how you apply Dijkstra's algorithm for a directed graph. We have already discussed the method for an undirected graph as well. So if you have any doubts, you can put them in the comment section below. I'll be reaching out to all of your doubts. So thank you for watching and meet you in my next video.